Today what we'll look at is exponential growth and decay, and if you've ever wanted a why do we need to know this kind of lesson, this is it at the moment. I'm teaching remotely because of the growing rate of COVID-19 cases here in Melbourne, and what we're trying to do is, this is what's creeping up at the moment. Okay, they're creeping up like this, and it's going to spread at an exponential rate unless we lock down, do all of that sort of stuff, i.e. flatten the curve, okay, and slowly, what we hope will be this. So it's a great lesson to sort of look at how the exponential model works, because I'm sure the government, well, I hope the government has looked into kind of a mathematical model that suggests, look, if we don't lock down schools or if we keep schools open, what would be the rate of transmission, etc., etc. So they've modeled all of these things. They've used mathematics to do this stuff, and the decision has been made to, in the end, lock us down. So what are some of the other ways that or things that follow an exponential or a log model? Population growth, bacterial decay, compound interest, radioactive decay, and cell growth. So the basic law of exponential growth can be written in different but mathematically equivalent forms. And one of the common forms that we see is A of t equals A0, we call this the initial, initial. So A0 is the initial amount, and A of t is the amount we have after a certain amount of time. And again, we can choose pretty much whatever base we want, but base E, remember, is the one that we want to use because it's easy to work with in terms of calculus. And then invariably, what we have is a K value, a dilation factor, to turn the graph into the model that we want. All right, so here's an example of obtaining the K value and then finding the half-life of radium-226. So after 1,000 years, a sample of radium-226 is decayed by 37% of its original mass, i.e. 63% of it remains. Given the rule for the amount of radium-226 can be modeled by this, AN equals A of 0, or A0 multiplied by e to the kt. So first of all, show that the K value is this. Okay, so what we'll do is note that the initial amount that we have, it doesn't say. That's okay, and it never matters in these questions how much we initially have. All we need to know is how much is left and what time period over which we have that much left, and then we can go from there. Watch this. So what we're going to say is the amount that we have left is 0.63 equals the amount that we started with, which is 1 unit. And all we do is we treat this as 1 unit, and we say that this is 37% of 1 unit, i.e. 0.63% remain, multiplied by e to the k. Now k is what we're trying to find out, t is what we know. So we're going to say 1,000 t, 1,000 k. Alright, now how did I get 1,000? Because that's the time after 1,000 years. Alright, so if we divide by 1, I'm left with 0.63 equals e to the 1,000k. Alright, how do we get the k value, or k by itself? You can see here that we switched to log form. So I'm going to go log e is the base, 0.63 is what I'm logging, equals 1,000k, k equals 1 over 1,000, multiplied by log e, 0.63, which is what I was required to show in the first place. Alright, so now what we are going to do is find out the half-life of radium-226. Now again, the problem some students have with this is that we haven't been given the initial amount and then how much of the initial amount is left. Now we know it's going to be half, but it doesn't actually matter. So all we do is we again just treat things in lots of 1 unit. Okay, so if this is our equation, so AN equals 1 unit times e to the, now the k value is 1 over 1,000 log e 0.63t. What we want is if I've got 1 unit of it to begin with, we want when a of n equals, or a of t equals 0.5. So that's going to be 0.5. That's half of the 1 unit. Okay, so how do we do this? Well, it's obviously the calculator. So we're going to go solve 0.5 equals 1 times, now we don't need to write that, but I can write it. Okay, we're going to go Shift E, Shift Divide, 1 over 1000 times Shift 5 for ln, 0.63, x, well, let's put a times x just to be sure. Now, make sure your cursor swings down from there, solving for x. All right, so we got that awful exact value, state it to the nearest year. Let's go to the nearest year, 1000, so we're going to say that t equals 1000.2034 ... Okay, therefore after 1,500 years, if we're going to the nearest year. Okay, so let's go to the next question. Show that k equals log 200 on 360 if can be modelled by this rule where t is the time in minutes. There are 4,000 bacteria present initially, which grow to 800,000 in 6 hours. Okay, so this does give you an initial value and the value after a certain amount of time. So let's use those values. 800,000 equals 4,000 times 2 to the kt. T is time in minutes, and we've got 6 hours. So 6 times 60 is 360, which is where that number comes from, obviously. 2 to the 360k. So again, we're finding the k value first of all. Oh, that's actually all we need to do. Okay, so now what I'll do is I'm about to divide. So I'll go now 4 goes into 8, 2, 0, 0 equals 2, 360k. Now we need to make k the subject, so we'll go to log form. Log 2, 200 equals 360k. K equals, so they've just divided by 360, so log 2, 200 over 360, and we found the k value. Doesn't ask us to do it, but therefore the model is going to be an equals a0, which was 4,000 times 2 to the log 2 200 over 360 t. Right, let's just see whether this does work. So we'll go 4,000 times 2 to the power of, actually we'll go just going to use the template here. Once you do this stuff here, it starts to become a little complicated. 2 to the shift divide. Now shift 6 log 2 200 over 360 x. Alright, now what we'll do is we'll put the 6 hours or the 360 minutes in, and what should happen is when we sub for 6 hours or 360 minutes, the bacteria should end up at 800,000. So let's do that, times 360. And there it is, okay? So when we put it in there, it works. Okay, this one here was on a Year 11 methods paper. A certain Sacré-Cœur staff member is well known for leaving food in the refrigerator long after its use-by date. The biology teachers measure an initial amount of 100 bacteria in a particular batch of food. This particular type of bacteria will double in population every 6.5 hours. The number of bacteria can be modelled by this, so they give us the growth function here, or decay function, whatever you want to call it, where t represents time in hours. Okay, show that k equals this value. All right, so what's going to happen is that we're going to start with 100 times 10 to the kt. Now, t is time, and time is 6.5 hours. That's 6.5, which is 6 12s, that's 13 on 2. So we're going to go 13k on 2. That's our time. And what does that equal? Well, the amount of the bacteria doubles, so it's going to be 200. Now note that I could just use that unit approach that we did last time, which is 1 unit grows to 2 units, and it's going to be exactly the same thing, because inevitably what we're going to do is divide by 100 here. So we are going to do that now, which is 2 equals 10 to the 13k on 2. All right, let's switch to log form. Log 10 to log 10 to equals 13k on 2. We're going to multiply by 2 and divide by 13. So k equals 2 log 10 2 over 13. K equals, now that 2 can go up there, and we can square the 2, which becomes 4. Log 10 4 on 13 as required. All right, let's keep pounding out these questions here. Radioactive substance is decaying in a lab. Initially 5 kilos of the radioactive substance was present, and 4 days later half of it remained. The mass R kilograms of radioactive substance at time t days after its place can be modelled by this thing here. All right, so we're just going to use that form. State the value of R0, the initial amount, that's 5. Show that the value of k is this, okay, so we have half of it remaining, so we've got 2.5 equals 5 times e to the, and t is days, and it's 4 days is the time, so we're going to go negative 4k. All right. So we divide by 5, which gives us 2.5 over 5, which is half, equals e to the negative 4k. Let's switch to log form. Log e half equals negative 4k. What do we need to show? So we're going to divide it, and it's, okay, so this, let's write this out. So k equals, so it's going to be negative 1/4 log e half. Now you note there that we've got log e2, and this is positive. So what we're going to do is bring that up there. So that's going to be k equals negative 1/4 log e2 to the negative 1. Okay, so that goes up there. That negative 1 comes out the front. K equals 1/4 log e2 as required. Okay, sketch the graph of R. Right, so let's write it out. R equals the initial amount, which was 5, multiplied by e to the, now this is negative, so it's negative 1/4 log e2 t. Alright, so how do you sketch this thing? Well, first of all, it's important to note that what we've got on our hands is a decay graph. Right, so decay graphs go like this. We've also got a domain restriction, t is greater than or equal to 0. So all we need is the y-intercept. Now the y-intercept occurs when t is equal to 0. Slam t is equal to 0, you've got e to the 0 is 1, 1 times 5 is 5. So we've got 5. So what would happen is it will swing in like this and go down here. All right. But what I'm going to do is just pick it up from there. And what it should do is run along the asymptote here, which I will put in. That should be a dotted line. So it goes along there. So assuming that I did it, I'll just change color for effect. There it is, running along that line there. And we're going to say that this is the R axis and this is the T axis. This is when R is equal to 0. There's our asymptote. Alright, so that is 0, 5, etc., etc. So there's our graph. To the nearest hour, how long after it was placed in the lab had 80% of the substance decayed, i.e. was there 20% left? Okay, so there's two ways of doing it. Okay, now what we can do is we can actually go down to the unit, which is times or one lot of, and then down to 0.2 or 80% of it, times, what's the formula? E to the negative a quarter log E to T. So we could do it like this. You could do 5 and then work out what 0.2 to 2/10 of 5 is. Let's just do that on the calculator. Oh, the calculator's not working. Just bear with me. Yeah, I've lost my cursor. Okay, sorry about that. 0.2 times 5 is 1. Alright, so you could do it like this. But just note that your first move here is going to be divide by 1. First move here is going to be divide by 5. And 1/5 is 2/10, which is 0.2. So it's exactly the same thing if you go to the unit. Right, so you can solve that or you can solve this. It doesn't really matter which way you go. Okay, to the nearest hour. So let's go a solve. 0.2 equals 1 times shift 4, shift divide, negative 1 over 4 times shift 5 for ln, 2x, comma x, please. So we're going to say that t is equal to 9.2877 ... So this is days. Okay, so this is 9 days. So we're going to say 9 days. Now, this is going to be the number of hours times 24 hours in a day. All right, and it's going to be either 6 or 7 hours. All right, now because it's decaying, all right, what if we go back to the 6, it's not going to drop below 0.2 or not going to drop below 1 if we round down. So we need to round this up. So it's actually going to be 7 hours, not 6 hours. Okay, so let's just scrap that there. So 9 days, 7 hours is our answer there. Right, so just watch your rounding on these type of exponential function questions or log function questions. Okay, it can be a little tricky. All right, I think we're going to see another example of how to round. Okay, a crystal is growing in a beaker. 2 milligram crystal was placed in the beaker and 8 hours later the mass present had doubled. All right, so it's modeled by this. So this is our function here. So our C0, the initial value, was 2. Okay, find the value of k. We're not showing it, we just need to find it. So we're going to go, if it's doubled, 4 equals 2 times e to the kt. T is 8 hours. Is modelled by this. I'm presuming that t is t hours. Okay, so we can use the t is equal to 8, so it's going to be 8k. Right, so we'll divide by 2. So 2 equals e to the 8k. Then we'll go to log form. Log e2 equals 8k. K equals 1 over 8. Log e2. No need for any show or any simplifiers on that one, because we don't need to show that it's in the form. We can just use it now. So c of t equals 2 times e to the 1/8 log e2 t. That's our function. Now, this value here, log e2 is positive, 1/8 of it, 2. So all it's going to do, it's going to be the same graph as the previous example, the decay function, except this one here is, or represents, growth. Okay, so let's draw our axes. And our initial value, 0 goes in, e to the 0 is 1, 1 times 2 is 2. So there it is there. So it would go like, it's going to come along here, go up and kick from there. So it's going to go up like so. Close circle, 0, 2. This is the t-axis, this is the c of t axis. Does it have an asymptote? Well, since t is greater than 0, greater than or equal to 0, technically it doesn't, but I'm just going to put it anyway, it doesn't really matter. It would exhibit asymptotic behaviour should it go to negative infinity, so I can put one in if I want. C of t equals 0. To the nearest minute, how long after the crystal was placed in the beaker was 5 grams of crystal present? So 5 equals 2 times e to the 1/8 log e 2t. Right, so I could also put 1 and 2.5, it doesn't really matter. Okay. So I could go the unit approach on this one, but because the numbers are a bit more clunky, I won't. Solve 5 equals 2 times, okay, shift 4, shift divide 1 over 8. I'm really careful with using all the templated options here, otherwise I put things in the wrong spot. Okay. To the nearest minute. Okay, so t equals 10.575 ... So it's 10 hours, because t is defined as hours. Now it's this minutes. So it's times 60. So it's going to be either 34 or 35. And in this case, it's going to be 35, because this is a growth function here. If I round down to 34, it won't be enough to get the 5 milligrams. So it's got to be to 35. So 10 hours and 35 mins. Okay, so I'm not rounding up because that's 0.5. I'm rounding up because 34 will be too low. And even if it was 34.02, I would still round to 35 in that case. Okay, another one. The number of parts per million X of E. coli in a stream T hours after a pollutant containing E. coli are introduced is modeled by a log function. So how many parts of E. coli are introduced into the stream? So that's going to be when time is equal to 0, we drop all of them in, and that's going to be log E 0, that's E to the 2, 2 comes down, 2 log E should really bracket that, equals 2. Therefore, 2 parts per million. To the nearest tenth of a part per million, how many parts per million of E. coli are in the stream when T is equal to 10? So that's just X of 10. Okay, F of 10. I was going to say I could do the exact value simply by plugging in 10 there, but they want it rounded, so that's cool. Okay, so X is equal to 2.855 ... So the nearest tenth of a part per million, so that's going to be 2.9 parts. So therefore 2.9 parts per million. Sketch the graph of X against T. Okay, so where is the asymptote? Actually, I'll stay on the line tool. Draw it in red. So what this is the standard log E function moved e to the 2 to the left. Okay, so if we're going to move it e to the 2 to the left, let's pop an asymptote in. And that asymptote is, so this is X of T versus T. And that's when T is equal to e to the 2. Now what's going to happen is the log function will look like this. It's going to go through 2. You already know it does that. And T is greater than 2. So what would happen is it would go up through there and come up through there. So it's going to go like that. Okay, 0, 2. We've got everything we need. To the nearest hour, how long after E. coli is introduced to the stream are there 4 parts per million? So 4 equals, what's my function? Log E T plus e to the 2. Alright, so what we want to do is solve for T here. So we're going to go into log form. So e to the 4 equals T plus e to the 2. T equals e to the 4, take away e to the 2. Alright, can't simplify that. Alright, it'd be tempting to go, oh, so isn't that just e to the 2? So we've got e to the 4, remove e to the 2 there, and there's no rule on common bases being subtracted. So that's our answer. And to the nearest hour, so this is going to be hours. So to the nearest hour. So that, oh, we need to round that then. So that's going to be shift e to the 4, take away shift e to the 2. So T equals so just checking the function, so it is hours, T hours, yep, to the nearest hour. Right, so T equals 47.209 ... Now, if I round this down to 47, what will happen is, actually, let's just try it. So if I go f of 47, because I've already got this function defined, I get 3.99, i.e. it's not 4 parts per million, okay? So we're going to go, therefore, after 48 hours, we will have 4 parts per million of E. coli in the stream, or at least 4. Okay, so another example. The volume of chlorine, C litres, in a swimming pool at any time T hours after it was placed in the pool can be modelled by this. The volume of chlorine in the pool is decreasing, so it's an exponential function, so it's going like this. Chlorine was 3 litres, 8 hours later, the volume, decreasing. Wow, I can read that. Right, so state the value of C0. C0 is 3. Show that this is the case. 2.5 equals 3 times 8 hours. So we've got hours and we presume that T is in hours then. T hours, yep. So that's going to be 8. Okay. So 2.5 is 2.5, which is 5 on 2. Divide by 3, that's 5 on 6 equals e to the 8k. Log e 5 on 6 equals 8k. Therefore, k is equal to 1/8. Log e 5 on 6 as required. Oh, getting messy. Explain how the model of the volume of chlorine in the pool shows that the volume is decreasing. That's a good question. So let's see what we're supposed to call this thing. C of t equals, the initial amount is 3 times e to the 1/8 log e 5/6 t. So how do I know that the volume is decreasing? Well, it's got to do with this value here. So what we're going to note is that 1/8 log e 5 on 6 is actually less than 0, i.e. this is a negative number. Okay, so what we presume then, and how do I know it's negative? Well, when you go e to the and you want a fractional or a number between 0 and 1, this means that it must be negative. So we'll say that is less than 0, therefore this is reflected in y-axis. So we're going to say that e to the x is reflected in the y-axis. So, and this is really an acceptable thing in methods. You can draw a graph of this. So e to the x looks like this, and when it's reflected, looks like this, therefore decreasing. Okay, so it's perfectly acceptable in methods to draw a picture. How many litres of chlorine were present in the pool 16 hours after the chlorine was added to the pool? Okay, so let's go C of 16 equals, so probably worth defining, shift define, f of x equals 3 times shift e to the, shift divide for the 1/8, times shift 6 for the ln, 5 on 6, times x, and there's my function, so f of 16 25 on 12 litres. Now why did that work out 16? 16 is 2. 2 goes there, which, so this is a good one to do by hand actually. I'll just show you how this works by hand. So I'll go C of 16 equals 3 times E 1/8 log E 5 on 6, 16. So that's the same as equals 3 times E to the 2 log E 5 on 6. Now what I've done is just gone 16 times an eighth, which is 2. Now I can grab that 2 and raise it. So I've got 3 times E log E 25 on 36, which log E undoes itself 3 times 25 on 36, which is 75 on 36, 12 and 12. So that's going to be 2, 1, how many times is 5? 25 on 12. There it is. All right, so a nice exact value question. So very much could be an exam 1 type problem on that. Okay, yeah. Right, to the nearest minute, how long after the chlorine was added was there 2 litres remaining? So 2 equals 3 times log E 1/8 log, 3 times E 1/8 log E 5 on 6 T. Okay, solve f of x equals 2 for x, please. There's the exact. So t equals 17.791 ... Okay, and this is minutes. So this is hours, is it? Hours. Okay, so hours. Okay, so we're going to go, therefore, 17 hours. Let's get the amount of minutes. So that times 60. So it's either going to be 47 or 48. In this case, it's going to be 48 mins because it's a decay function, and 47 minutes will mean it won't decay enough to be 2 litres remaining. It will be slightly more than 2 litres. Okay, so 48 mins will take it to less than 2 litres remaining. Okay, this example here, we're not going to do that. Okay, we've done this already. This is a half-life question, so we're not going to bother working out the half-life. I think the first example that we did was one of these. So let's do this one here. Assuming that the population growth is exponential, the population of Deer Park was 10,000 at the beginning of 04 and 17,000 at the end of 05. Find the population at the end of 2017. So what we need to do is get our function written and then work out what it will be at the end of 2015. So the beginning of 04, so here is 04, that's the first year, okay, and that was 10,000. And what we want to do is we're going to have 05, 6, 7, 8, 9, 10, 11, 12, 13, 14, end of 15. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 full years this happens. Okay, so that's going to be the time. Okay, so what we can do is get the k values. So we can choose how we want to write our functions. So I'm just going to write a of t equals a0, the initial, times e to the kt. Okay, this is the function I'm going to use. Now, so it was 10,000 initially, 17,000. So we're going to go 17,000 equals 10,000 times e to the 12k. Uh, 17 divided by 10, 1.7 equals e to the 12k. Log e 1.7 equals 12k. K equals 1/12 log e 1.7. So you could have chosen any base you wanted there. I just like base e. So now let's write out our function. A of t equals the initial, which is 10,000, times e to the 1/12, I'm going to run out of room here, log e 1.7 t. There's our function. So now what we're going to do is find out what a of So in what year will it be double? So A of t equals, we want to find out when A of t is double that of 20. Find the population at the end of 2017. So that is going to be, not A of t, that's going to be A of. So 15 was 2015. Oh no, 12 was 2015. Oh goodness. Okay, let's just type this into the calculator. Sort of get confused with these number of years between type questions. Shift 7 equals 10,000 times shift e to the shift divide for the 1/12 times shift 5 for the ln x. Okay, now f of 1 should be 10,000. Oh no, f of 0 should be 10,000. Good. Now f of 12 should give us 17,000. Good. So that would be end of, f of 12 gives us the end of 2015. So f of 14, or a of 14 in this case, equals 18571.93 ... Okay, to the nearest 1,000 people. So this is to the nearest 1,000 people is going to be therefore 18,571 people. Okay, to the nearest 1,000. Units, tens, hundreds, thousands. So am I allowed to round that? Yeah. So this is not rounded to the nearest 1,000 people. So this should be, so there's thousands. This is actually going to be 19,000 people. Okay, so find the population. There you go. In what year will the population be double that of 2015? So this is going to be, so A of t equals double that of 2015. So 2015 is that. So it's going to be 34,000. Okay, solve. 34,000 equals f of x. Solve for x, please. So t equals 27.675. All right, that then is therefore t equals 28. So here we go. This is going to take some calculating. So 2017 was 14. So add another 14 to get to 28. Add another 14 on this. So that's going to be 2031. So in 2031, this is going to happen. All right, now to the final one, and I've actually recorded a video several years ago now of this problem here. It's been around since I was actually in Year 12. I remember doing this one, but it's brutal. Okay, so I'll link in the red kangaroos, grey kangaroos question in on Google so that you know where it is. So your modelling questions will be those ones there.